Hi, everyone. I'm Waleed, currently at Stripe. My job title is Professional Git Hater. So I'm assuming, how many people in this room have a monorepo for their org? Raise your hand. Okay, so we're going to talk a bit about monorepos and what I don't like about Git. Do we have anyone who commits to Git, like Git contributors? Kind of, okay. Anyone for Sapling, Facebook, Meta? Okay, so this is all kind of hearsay in the sense that I didn't talk to anyone at Facebook or who works on Git. So take it with a grain of salt, but it is based on my experiences over several years trying out different different data structures, including Git and Sapling. And I'm just going to walk you through one of them and maybe point out some ways that Git could be a little better. So probably most of you are familiar. There's the Git object model. It has 4 types of objects: the commit, the tree, the blob, and then nobody uses tags. But they're there. And it looks like this. You'll notice like the trees can contain other trees in them or blobs. It's this Merkle tree. And fortunately, we had a good discussion of that. And the commit will contain, one tree and some number of parents. So you can imagine to store this on disk, it's like a pretty simple conceptually, just a mapping from like object ID to a file in its most simple form. And then there's all this stuff about pack files, which get in the way of forming a coherent mental model, but you get used to it. And if you're like us, then GitHub is spending like hours a day recomputing its pack files, which is really frustrating. So what if, there's a better way to do things? That's the question. So here's one specific operation, merge base. The operation computes the nearest common ancestor or lowest common or whatever. So can anyone tell me, has anyone been grinding leak code and can tell me what's the algorithmic complexity of an operation like that in a binary tree? Anyone? Raise your hand, shout it out. Nobody's run. Yeah, that's true. I guess this is the wrong era to ask. If you don't answer, I'm going to make one of my teammates call or answer. All right, log in. Not quite. So the way, it could be log in if you do it right. But the way leak code probably has you do it is just take both nodes in this tree and then traverse their ancestors and keep track of which ones have been visited. And if you ever see one that was visited while you're going up in the tree, then that's a common ancestor and it should be the nearest one. And it depends on what your tree looks like, how long this operation is going to take. And this operation happens a lot in Git. For traversing history, like if you just want to know, what is the stuff on this branch, you have to know where the branch ends, right? 3-way merge is really important. If you do git merge, you compute the diff on one side and the diff on another side, and you have to know what those sides are. And object negotiation, that's like in git fetch, figuring out which objects you have and you don't have. You want to figure out a common ancestor of both sides and just transmit what has changed. So Git claims to solve this via the commit graph data structure. Has anyone heard of this? Okay. Also not our Git people, so you can't complain too much when I talk about it. So this is a thing I took from some Microsoft's blog post. So ignore the fan out. It's just a kind of index. This commit graph data structure has a list of commits. Firstly, this is a sorted table, like sorted string table. And each of those indexes essentially points into this other table of commit data. And for each row, we have a tree ID, we have the date, we have the first parent. We might have a second parent. We might have nothing if it's not a merge commit. If it's a crazy commit with 100 parents, they store it somewhere else, which is wise because nobody should be doing that. So this should be an uncommon case. So what are the problems with this? I think there's a couple. I haven't fully benchmarked this to verify exactly, but one of them is there's a bunch of junk here. So the tree ID is at least that's 40 bytes of just data that's not useful for computing the merge base. There's also the date. I don't even think that should be in there. I'll talk a little bit about that. And then the thing that's important for computing a merge base is you're going to walk the parents over and over again. You're going to take whatever this ID is and you're going to jump to that row in the table. And when you do that, there's no guarantee. In fact, that parent row probably won't be anywhere near the row you were just on. So you're going to jump around this table a whole lot, and that's fine asymptotically, but not so great for stuff like caching. The tree ID, the big junk there, it'll also be better for caching if you can fit a lot of IDs in your cache lines and not have all this other junk data. So I think it's a mistake to have done it this way. I think they should have gone a little more columnar and made it more dense so that they could traverse these edges more efficiently. So now that we have this data structure to augment our lookup, how does that affect the complexity of our nearest common ancestor lookup? It was O of n before. Yeah, same, yeah, O of n. All right, so I'm not impressed. This didn't actually improve the algorithmic complexity of this operation. So what does the git commit graph try to do instead? It has this thing here. This is from the docs. Does anyone know what a generation number is? Basically a generation number, you assign it to a commit. Specifically, it's either the the deepest or shallowest ID that you can give to that commit. So if I'm generation number 0 and I have 2 children, each of them have generation number 1. Git has 2 notions of this. I think that's a mistake. One of them is strictly topological, and one of them is this crazy thing it does with the committer date, corrected committer date. I don't like it. But the idea is there's this property here. If you search for long enough and you're still not finding a common ancestor, then you know those commits weren't related. And you just look at the generation numbers and you do a cutoff a little bit earlier. So what does that get us to complexity-wise? It's still OFN. So I'm not very impressed for yet another reason by this data structure. This whole data structure, it definitely improved stuff, but I think they could have done better. This is the last thing I'm going to mention. Git loves doing this thing where you append a bunch of things to a chain of objects of like exponentially increasing size, and that's how they manage the addition of new things to this immutable data structure. At my work, we are dealing with pack files doing kind of the same thing, and Git constantly recomputing them. I don't like this just because it's hard to reason about and maintain. It makes the performance kind of unpredictable because you might trigger one of these operations, like when you just add some arbitrary commit and it goes over a threshold. So I'm not a fan of that. So I'm going to talk about what Sapling does better. So I did not work on Sapling. I worked at Facebook and I worked next to the source control people though. And I've looked at their library that they published standalone to implement one of the data structures that they use in Sapling to support the merge base operation. So there's a really good set of slides here and docs, and you can find all of this stuff on my website when I post this presentation later, waleedkhan.name. And you can even look at the library implementation there, which is permissively licensed. So here's the basic idea. Most of your commits are going to be in a straight line. There's not a very high branching factor. And if you're Git, you don't make any assumptions about what the commits look like. You're prepared for a really weird commit graph. But realistically, if all of us are doing monorepos, we probably have like a big main branch that's pretty much just linear mostly. And that means you can compress the structure in a very efficient way. So if you have like 5 adjacent commits with nothing in between, no merges or anything, you can just number them and you can say, well, we have a bunch of commits from 1 to 5. And you can store the mapping of ID like 1 to the commit hash somewhere else. So we're exploiting the low branching factor that in practice we see for our source control graphs to have a better data structure. There's more details in the slides, but this is basically what it looks like. For segments that have at most 1 parent in them, you can store them contiguously, and then you have to have each segment have any number of parents. So basically, the size of your graph is condensed to the number of merges in your graph instead of the size, the number of nodes in the graph. There's more to it than that in Sapling, and you can look at the slides or I can talk to you about it later. But it's basically just add a couple of layers of hierarchy. These are some benchmarks, and you can go directly to this commit to check the benchmarks. They have it on several repos, I think including some internal ones. So this line here, ancestor of x, x, that means find the merge base of a commit with itself. That's very fast in all of the implementations they tried. But then x, y, they're looking for the merge base between Linux like 2.6 and 5.8. With their approach, it takes 0.1 milliseconds. With the old Mercurial approach, it took 10 milliseconds. So that's like 100 times speed up. And it performs very well in practice. I've personally used this library for my own Git tooling and found that it performs very well for that. So here's some additional data that I just stole from their slides. One thing is they keep metadata out of line in separate places. A lot of it is not even on the machine, but the segment thing is actually small enough that you can just store it on the client side. So you can keep a lot of the important data about the structure right at hand and then just query the metadata later when you need it for the end results of whatever you're doing. So this is better, I think. They've actually split up the different pieces of data and they've decided some of it lives locally, some of it lives remotely. And here is the underlying data structure. It's an append-only log structure, and you can read about it there. It's pretty interesting. It's optimized for the case of like your keys are all evenly distributed. There's a prefix tree thing. It relies on having a radix tree, but overall, I like it a lot more because it doesn't need this repacking procedure that you see in Git. And I really recommend checking out the internal documentation for Sapling for ideas about source control. And like we saw, the data structures are better. It scales more with the merges of the graph. They've compressed the data where it matters. And they have like substantially improved performance for the operations that they're trying to support, unlike Git. So that's everything. I just wanted to show you that Git is not the end all be all. You can make better choices than Git and you can reap the improvements if you are careful enough. That's all.